The things about strong transitioning storms, the footprint of heavy rain is bigger than with your regular storm that just tracks has no front with it. There are two composites. This probably, since it's a composite, underdoes the amount of the very heaviest rain. But the idea is your footprint of very heavy rain on this guy is going to be much smaller than it is on the other guy. And it might be that you get different footprints. A footprint here, depending on the time of day, another footprint somewhere else where you have a very more localized extreme rainfall event. Contrasting storms, let's do Bertha. These are both North Carolina baby doll storms, right? Both of them, it was North Carolina hit. I think they hit the same, no, Fran hit them. Was Bertha and Fran or Bertha and Floyd? I don't remember which years. But anyway, this one's a non-transitioning storm. This one's strongly transitioning storm. Let's look at what they look like. First, Bertha. Here's Bertha at landfall. The storm's here. What can you say? The upper level jet's way back over in here. So at this particular time, the heaviest rain is pretty much on the east side of the storm. As it gets further north, it finally starts to, and one of the things you can look at, these are the isotherms at 850 millibars. You don't see very much packing, not any evidence of a front. As this trough starts to come closer, starts to get a little bit of a negative tilt. It's still not great, but you start to finally see a little bit of packing of the isobars, of the temperature building. So you're getting some semblance of frontogenesis. Upward warm advection, that's good for upward motion. Floyd, back in here, here's Floyd, a huge storm, big circulation. Already back at this time, before it's even on shore, there's warm advection across North Carolina. It's in the entrance region of a jet. Here's the wind speeds. This is the jet. Back in here, there's a long stream variation, so there's upper level divergence going on in there. It's already raining heavy over North Carolina before landfall even. Yeah?
Was Bertha the earliest Cape Verde storm in record, do you remember? It had to be close. It was like July 4th.
I don't know. Josh, was it?
This is definitely one of the earliest of the last years.
Yeah, that's stuck out. Really?
Which Bertha are we talking?
96.
96.
July
That one
96.
too.
This one was,
It hit North Carolina.
yeah.
They were both early.
They were, yeah, that was a Fran year, right? 96?
Yeah.
Yeah, Fran was also.
But you look at this one, back in here, already front, but with time, as the trough comes over, this long stream variation gets stronger, the front gets stronger and stronger, and actually the warm advection now is getting up back in here, rainfall way out ahead of it. A big goofy looking footprint. I should have had radar for it, but I don't, because I couldn't have too many. But here's the rainfall. Bertha, east side maximum, east side maximum. It starts at transition where it starts to develop its front. Now everything shifts to the west side, the heaviest. Fran, big storm, huge rainfall, flooding from down here, pretty much all the way up to New England. Everybody flooded. A great weenie storm if you like heavy rains. Speaking an analog, I put this in because this particular site is something that anybody can look at. You can actually go in and for any event, and HPC has this thing where you can actually get it. It'll pick out similar events, and then you can go back and look at the track and the rainfall footprint. And then these are the things that Dave Ross says you should look at. Size is important, how fast it's moving, vertical winds here, blah, blah, blah. But anyway, you can actually look at this particular site, and you can get an analog for the event. Another contrasting storm, Hugo versus Fran. These are storms that my friend Andy chased both of them. One of them he got his car blown, windshields blown out. The other one he had the roof of the motel blown off. But you notice something about Hugo. Hugo is pretty good down here, It does have some rainfall back in here, but it doesn't have, it's not near as heavy as back in here as Fran. One of the differences is certainly speed. This guy goes from 1 day movement is from off the coast to back up to Lake Erie. This one's 1 day movement is from the North Carolina-Virginia border to just south of Pittsburgh. So certainly speed of motion makes a big difference. But also, you want to look at what's happening to the upper air and the storm itself, circulation. Fran keeps this nice circulation as it moves north. It's got deep flow into the mountains, deep flow into the mountains. What happens to to Hugo? Back in here, doesn't have any easterly flow into the mountains anymore. At 850 or 500, it's actually parallel to the mountains, so it doesn't get the upslope. It's already starting, the storm's already starting to shear apart, so you're losing its tropical characteristics and also losing a lot of the rainfall and lift. It's not a typical, a lot of transitioning storms do better. This particular one never, it just sheared. It really didn't transition to a good extratropical storm.
Didn't you go take a left-hand turn over, go over Charlotte? It was supposed to come up, because I know I live in Central Virginia, and they had forecast the night before was coming right up over us, and they canceled everything, courts and all.
Well, I think actually they expected it to curve and it didn't. I mean, the ridge, the subtropical, the ridge to its north was so strong that it just kept clipping. And it kept moving pretty dang on fast because of that. Oops. Sorry. Evolution, here's the surprise. One of the surprises. This is Aaron. Aaron's a storm I talked about that came into Texas, and it becomes a tropical, has 70-mile-an-hour winds in Oklahoma. Its maximum rainfall is right at 6Z. In terms of why did it, a lot of storms tend to increase at night, especially when they're weak like this. That, if you get close to the mountains here, that's the time where the low-level jet is strongest, around 6Z, 6 to 9Z. So you're getting an increasing low-level vorticity because of the jet on here and on the east side. You get, during the night, you get, this is PV, potential vorticity. Think of it, it's both static stability and vorticity, but for us, we'll just think of it in terms of vorticity. You can see here, at 0Z, it's not as strong as this. You get an extra light blue shade in here. So it's actually increasing, wind speed increasing at night. One of the things that it did is it got some help from this little booger up here, an upper level trough. So part of the reason it increased its low level circulation is a convection. Convection got going and that helped. But also it got extra upper level divergence because of an extra tropical little wave that went back to the north. So that's one of the things you always want to worry about a little bit. This one was a very big surprise, and for any of you who didn't remember seeing this on the thing, there's a circulation, there's the eye, there's the winds, sustained 70-something, pretty much hurricane force gusts, and the pressure trace. Really pretty dramatic, and that's one of the kinds of surprises you can get. You can get surprises that storms, they can't get back to hurricane intensity usually, but they can get back to tropical storm intensity during night.